This is Chapter 21, Problem 23 from the 9th edition. So in this problem there are two charges, Q1 and Q2, that are on the y-axis, an equal distance from the x-axis. Partway out along the x-axis is a particle Q3. All of these charges are positive, and that's why I've drawn them all as blue. Using color is one of the ways to help me solve things, so again, by sticking with blue, then I can easily see that all of these forces will be repulsive, and so on. So that's one of the things that I will do consistently. So again, the distance between each of the particles and the x-axis is called d in the problem definition. And the distance that particle 3 is from the y-axis is called x. So we're given the values of these charges. Q1 and Q2 are equal. And x can go from 0 to 5 meters. We want to know where the net force on particle 3 is a minimum, where the net force on particle 3 is a maximum, and what those maximum minimum forces are. These are the four things that we want to find in this problem. Before we do any math at all, there's a few things we can determine. First of all, if we look at the case where x is 0, then we can see because Q1 and Q2 have the same magnitude and they're the same distance apart, then by definition, by the symmetry of the problem, there's no net force on particle 3. So that means we've just answered parts A and C of the question. At x equals 0, the net force is 0. In the textbook, most of the problems that have several parts to them will have some parts that can be solved completely without doing any math at all. Keep that in mind. Now we also know that anywhere along the x-axis, that the net force will be just along the x direction, since again, Q1 and Q2 are equal charges and they're both equally distant from the x-axis. Because of that, and because the contributions are equal, then to calculate the net force, all we have to do is calculate the net force from one of the particles and double it. So now, looking at the calculations, if we look at the triangle just representing Q3 and Q1, for instance, then we have, again, the distance from the x-axis to Q1 is d, the distance from the y-axis to Q3 is x, we can call this angle in here theta, and the hypotenuse of this triangle, the distance from Q1 to Q3, is the square root of d squared plus x squared. If we look at the force on Q3 from Q1, then the magnitude of that force is proportional to the length of that hypotenuse. The x component of that force is proportional to the length of this side, and the component in the y direction is proportional to this side. So as we go back and forth between these two diagrams, these two similar triangles, the ratio between the distances and the forces will be the same. So, the x component of the force on particle 3 from particle 1 is the magnitude times the cos of that angle. The cos of that angle from the similar triangles is x over the square root of x squared plus d squared. So we can fill in what the magnitude of the force is from Coulomb's law, and so we get the net force in the x direction of particle 3 on particle 1, on particle 3 from particle 1 is this. So the force will be a maximum or a minimum when the derivative equals 0. And so if we differentiate that equation and set it to 0, we can find out when the force is a maximum or a minimum. Now, this simplifies because all of these terms are constants and none of them is 0, so that we can factor this out so that for this whole thing to equal 0, this will have to equal 0. We can apply the quotient rule in calculus. If this top we call f, and this is g, then the quotient rule says f prime g minus fg prime over g squared is the derivative. So f prime times g minus f times g prime all over g squared is the derivative. And we set that equal to 0. So now, when we go ahead, again, the bottom, the denominator, can never be 0, because as long as d is positive and d and x are both real, then the denominator can never be 0. So all we have to worry about is when the numerator is 0. So we can go ahead and perform the differentiation. And so we get this because realize that this term, d squared plus x squared to the 3/2, and this term, d squared plus x squared to the 1/2, have a common factor of d squared plus x squared to the 1/2, which we can factor out. So now, when we go ahead and do the algebra, very simply, we wind up with the situation that x squared equals d squared over 2, or x is plus or minus d over the square root of 2. From the problem definition, we were interested in solutions for x being positive, and so we reject the one where x is minus d over the square root of 2. So the solution we're interested in is the one where x equals d over the square root of 2. Since we said, again, in the original definition, that x could go from 0 to 5 meters, this solution will be valid if x is less than 5 meters when we solve it. So if d is 17 centimeters, as in the definition, we get a value for x of 12 centimeters, which is valid. So the net force on particle 3 from the other two, as we said before, is 2 times the force of particle 1 on particle 3. So when we put these in, you can do the calculations because now each of these quantities are known, so you can determine the numerical answer. And this answers b and d. B is 12 centimeters. D is the answer to this equation. So now, as a check, what we can check to see is verify that that force is a maximum rather than a minimum. Well, to do that, there's a couple of things that we know. First of all, we've shown that the force is actually 0 at x equals 0. We also know the electrostatic force goes to 0 as the distance goes to infinity. And because the charges are all positive, then we know that in between, the force is always positive. So since it's 0 at both ends and positive in the middle, then by definition, F must be a maximum at this point in the middle.